And our next presentation is dealing with the topic PEM, Electrolysis Development at Juelich Research Center. Welcome here with me, the head of Department Electrolysis from the Forschungszentrum Jülich, Mr. Jürgen Mergel.
Okay, so thank you for the nice introduction and welcome you at Hannover Fair. So I will give you a short overview about PEM electrolysis and before I will give a short introduction and also a short introduction about the difference between alkaline and PEM electrolysis and the requirements for electrolysis by coupling the electrolysis with renewable energies. And what especially that means for the challenges for the further development. Okay, so Juelich Research Center is one of the biggest centers which are funded from the German government and the state of North Rhine-Westphalia. So we are around 5,200 people which are working on different research fields, and I'm located in the Department of Energy and Environment. Next slide, please. And in our institute, the IAK 3, our R&D topics, besides the fuel cells and the gas separation and batteries, are hydrogen technologies, especially the water electrolysis. On the PEM electrolysis at the moment are around 25 people working from the catalyst up to the whole system. As you know, I think there are three different parts of electrolysis or types. The alkaline electrolysis with KOH as an electrolyte, the polymer electrolyte membrane electrolysis, which are our focus now in development and research, and we are also involved in the high temperature electrolysis development. In my presentation I will focus more on the PEM. So if you compare, please next one, the alkaline and the PEM electrolysis, the big difference is the current density. Alkaline, normally you operate with 0.2, 0.4 amps per square centimeter. The PEM electrolysis at the moment is running between 0.6 and 2 amps per square centimeter. Next. And if you look at the cell area, so this is around 1.8 square meters, and in the past alkaline electrolysis was built up to 4 square meters. At the moment PEM electrolysis is in the range of 300 square centimeters. The megawatt scale stack from high hydrogenics, this is 1,400 square centimeters, but at the moment commercial products are 300 square centimeter. Next one. And if you look at the hydrogen production rate, this electrolyzer at the moment produces around 760 norm cubic meters per hour, and the biggest commercial system at the moment from proton on site is in the range of 30 norm cubic meters per hour. And if you look at the lifetime, this is very important, especially for the costs of ownership. Alkaline is in the range of 90,000 hours. PEM, let me say, is in the range of 60, but at constant load, at constant operation, not at dynamic operation. Next slide, please. So, and if you look what I have mentioned before, at the same cell voltage efficiency, like 1.8 volts, this is approximately 70% depending on the higher heating value. The current density for PEM electrolysis is much higher than for alkaline electrolysis. Normally, at the moment, PEM electrolysis is working up to 2 amps per square centimeter. If you go especially to Gine, you will see current densities which are going up to 3, 4, and 5 amps per square centimeter. And this is one of the advantages of the PEM, that you can run the PEM electrolysis at much higher current densities as with the alkaline electrolysis. Next slide, please. So the advantage you can see here, but I will focus more on the challenges. And especially for the PEM, we must reduce the costs, the investment costs for the electrolyzer, for the stacks, and also for the whole system. And if you couple this with renewables, we think that we must increase the long-term stability, especially when you run your electrolyzer in a dynamic mode with many start-stops and with many start-stops I mentioned before, but with many times where the electrolyzer didn't run. And what we need also, we must scale up the stack up to, for the megawatt scale, in the 2,000, 3,000, 4,000 square centimeter scale. Next one. Okay, so we have made a calculation, or the Ministry of Research and Development, that if you go to more renewables in the energy generation system, you need a system for storage the energy. And the results of this analysis, please the next one, show that at 2050 you need an electrolysis capacity to store the energy by hydrogen or by methane, if you make power to gas by methanation, of around 40 gigawatts electrolysis. And the next slide, please. And that means that the electrolysis or the electros units must be in the megawatt scale, or Siemens is thinking about gigawatt scale. And what does it mean also for the electrolyzers? If you store the hydrogen in caverns, the electrolyzer should run at higher pressures to pressurize the hydrogen up to 80, 100 or 200 bars to store the hydrogen in salt caverns. And also one requirement, I mentioned it, is the high dynamic and also the standby operation. If you look at this power range from for summertime out of this was a simulation for let me say a wind-powered renewable energy system. So you need around surplus power of around 80 gigawatts for electrolysis to produce hydrogen as an energy storage medium. And if you look at the rise of the sparks of the energy, that means also you need very shortly or a very short starting and stopping of the electrolysis. Next slide, please. And one advantage, I mentioned it before, if you go especially to Gino or to Proton, one possibility is for the PEM electrolysis, next slide please, that if you run the electrolyzer at a nominal load of 2 amps per square centimeter, you can run the electrolyzer with a PEM also at higher current density. But, next slide, that means also that you must pay a toll for the overload if you look at the efficiency. So if you run the system in an overload mode, like 300%, this is possible with PEM electrolysis, so you will have a loss in efficiency. But you don't need large electrolyzer units, you need only small electrolyzer units, which are possible to run also at high current densities. And the next slide, please. If you look and they called it GINA as an advanced PEM electrolysis unit. This was presented at the last DOE meeting in 2013. Then you can see at 300% overload. If you run this at 2 amps per square centimeter, the efficiency is greater than 70%. And this was for us the motivation to go into PEM electrolysis. Next slide, please. But the other one, I told it before, are the costs for the high hydrogen. And when you look at the production costs for hydrogen, normally the main factor is the electricity price, is the most important variable which influence the high hydrogen costs, and then followed by the electricity use. That means by the efficiency, and the third is the capital costs. That means the investment costs. But this is when the stack runs or the system runs 8,000 hours per year. When it only runs 2,000 or 4,000, what is normal if you connect this with renewables, the investment cost will more important. And for this, we are thinking about what is the right instrument to reduce the investment costs to come to lower production costs for the high hydrogen as at the moment. So at the moment we are in the range of 4 to 8 or 4 to 16 euros per kilogram. And if you compare this to steam reforming, this is much cheaper. Okay. So we have made a cost analysis and looked for, let me say, a technique. If you build up electrolyzers in the megawatt scale 2015, alkaline and also PEM, and we found if you run this at 2 amps, the PEM and the alkaline at 400 milliamps per square centimeter, the investment costs are quite the same. They are in the range of 1,500 euros per kilowatt installed capacity. And this depends, the high costs here also by the PEM, by the high catalyst loading, in the range of 2 to 6 milligram iridium, normally at the anode side, and platinum 1 to 2 milligrams and the cathode sides, and also on the titanium, which is needed inside the electrolyzer, depending on the high overvoltage at the anode side. And but if you go to, let me say, hydrogenics or to proton and ask for an electrolyzer, you will never get this electrolyzer for 1,500 euros per kilowatt installed capacity. And this depends on the, at the moment, lower current density. So, and this is at the moment normally at 1 amps per square centimeter in commercial products, and also at lower temperatures, depending on the, let me say, lifetime. And if you calculate, therefore, the investment costs, so you have only 50% of the expected current density, the investment costs will go up to 2,500 euros per kilowatt installed capacity. But, next slide. If you reduce the catalyst loading, increase the current density, and replace titanium separators, titanium current collectors by cheaper materials, we think that it is possible that you go down in 2030 down to approximately 600, 500 euros per kilowatt for the alkaline and for the PEM electrolysis. And when you, oh sorry, go back please, back, okay. And when you build up the power supply systems in this range that you can run the electrolyzer stack also at threefold overload, so the investment cost will be higher. But if you relate this to the overload, we think that it is possible to reduce the investment cost down to 200 euros per kilowatt installed capacity. And what does it mean if you look at a renewable energy system? From our model, we need 80 gigawatt electrolysis in 2015. And that means that the installed capacity is only around 35 gigawatts, but these electrolyzer units are able to run also in an overload regime. Okay, so this is our approach why we develop the PEM electrolysis. So next, and therefore we installed an industrial cooperation project together with Max Planck Institute, which are involved in catalyst development. We are working together with Fumatech also here on the with a booth developing new membranes. We are working with Solvicor. They are commercial CCM, catalyst-coated membrane developer and manufacturer, and also with Grebner Machine Techniques. They are responsible for separator plates. And our goal is in this project to reduce the catalyst loading by a factor of 10, to reduce the costs for the separator plates. That means we will replace the titanium by stainless steel, and we would like to scale up the single cell area greater than 1000 square centimeter. We call this project Electrolysis, okay? And if you look in the literature, so PEM electrolysis started in the 70s of the last century with very high loading, 6 milligrams for both electrodes. At the moment, you will find data in the literature, catalyst loading for the anode in the range of, let me say, 1 milligram, and for the cathode in the range of 0.2 milligrams. But this you will find in the literature, not in real products. If you look at the performance with this loading, this is very good. So with 0.2 and less than 1 milligram per square centimeter for the anode, you can reach current densities of 1 amps per square centimeter at cell voltages which are in the range of 1.6, 1.65. But this is with Neptune 1112 with very thin membranes, and that means that the ohmic losses are very low. Next slide. And what we have shown now, or what we have done, so we have reduced in this CCM, in this catalyst-coated membrane, the cathodic loading. So we are normally working with anode loading 2 milligrams per square centimeter approximately, and we have reduced the catalyst loading with a commercial catalyst down to 0.4 and 0.2, and we have done this also with a so-called core shell catalyst, and you can see we get quite the same performance as with a catalyst loading which is by a factor of 5 or 3 higher than we have here in this catalyst-coated membrane. We did this also for the anode. Please, the next one. This is not so easy. We did this together with Solvicor. The black one, this is our benchmark CCM, normally with Neptune 117, and we reach as 80 degrees centigrade at 2 amps around, let me say, 2 volts cell voltage. If you reduce the catalyst loading on the anode side by a factor of 2, going down to 1 milligram, the performance is not so good. But if you change the catalyst to a more active catalyst, so this is a new catalyst, iridium oxide, supported on a titanium oxide, you get quite the same performance as with 2 milligrams. But the question for us is, what does this mean for the long-term stability, especially in a dynamic operation? Okay, next one, please. So if you look at the over potential losses, you can see that the main losses in an electrochemical cell for an electrolyzer are the activation losses and the protonic losses through the membrane and inside the catalyst layers. Next one, please. And the mass transport losses and the electric ohmic losses are only for the separator plates and current collectors, but the activation and protonic ohmic losses, next one please, are inside the catalyst layer and membrane. And in the next slide, you can see what happened if you use thinner membranes, or if you increase the temperature from 50 to, next one, to 80. You see that the activation and membrane losses will decrease. Next one, please. And here you can see a real current voltage curves. So we started at 30 degrees centigrade and up to 80 degrees centigrade, and you can see at an efficiency of around 70%, you can double the current with increasing the temperature. Okay. If you go only to the membrane ohmic resistance, you can reduce this by decreasing the membrane thickness. If you go to an F1 115, that means from 200 micrometer down to approximately 120. Next one, you can see that the effect is much higher than with the temperature. So 80 degrees centigrade, an F1 117 is around 200 micrometer thick. If you go to an F1 112, you can also increase the efficiency, as you can see here at 2 amps per square centimeter. You can increase the efficiency by a factor of one third from or 1/4 from 74 up to 84. Okay, but what does it mean for the Faraday efficiency? And the Faraday efficiency is very important, as you can see in the next slide. So normally you will have high hydrogen losses through the membrane by diffusion, by permeation, and by the differential pressure. And what you can see here, this is the hydrogen concentration inside the oxygen compartment at different current densities. So we remember working range is around 250 up to 2 amps per square centimeter. With a thick membrane F1 117, we are below 1% hydrogen in oxygen. With an F1 112, without recombination catalysts on the anode side, you will have concentrations about 1% in the high current range. If you go to lower current densities, it will increase up to 2%, which is very critical by explosion. So where normally the lower explosion range for hydrogen and oxygen is 4%, and normally you must shut off your electrolyzer at 2%. Next slide, please. So, and if you increase the pressure, you can see here what happened with the cell efficiency. Normally the cell efficiency is a product of the cell voltage efficiency and the Faraday efficiency. At ambient pressure, you can see the Faraday efficiency, so the hydrogen losses are very small. If you increase the pressure up to 30 bars, which is normally a technical pressure, in electrolysis, you will have, especially at low current densities, a very low Faraday efficiency, and you can see the total cell or stack efficiency is in the range of 85% at 30 bars. If you compare this with ambient pressure, is in the range of 98%. And if you increase current density, depending on the ohmic losses, the overall efficiency will decrease down to 75%. Next, please. So, and if you look at the different membranes, so you must switch to, you can see, go further. If you go to very thin membranes, you can increase. If you go to higher current densities, especially higher than 2 amps per square centimeter, you can increase the total efficiency by this very thin membranes, Naphthalene 112, which are in the range of only 60 micrometers. So our approach is to reduce the catalyst loading and also to go to higher current densities to reduce the overall investment costs. Okay. But the disadvantage of this approach is that you will have a very high permeation rate from the cathode side to the anode side. And normally you couldn't run this without, let me say, a recombination catalyst inside the anodic compartment, or with some, let me say, permeation or diffusion barriers on the membrane side. This is one of the disadvantages if you go to higher pressures, especially in the differential mode. And on the last slides, I think you can see what we have now reached in our first stack. You can see at our booth. This is a 100 square centimeter stack, the first which we built in Jülich. We run this with a normal CCM, that means with a high cathode and anode loading, but we get quite the same cell voltage as we reached in our single cells at 80 degrees centigrade without titanium separator plates inside this stack. And in the last slide, I think we can skip this, but in the last slide I would like, or I must thank for the financial support of the Federal Ministry of Economics and Technology and also the Federal Ministry of Education and Research. And I would like to thank you for your attention. And I would like to introduce my work and our work also, if you are interested, at booth 66. Thank you.